All right. So we talked about interaction diagrams, that they describe the failure surface of a column loaded axially and with moment and bending. So now we're going to draw an interaction diagram. How do we draw an interaction diagram? We're going to select a strain profile. Right? Think back to very beginning. This is all it comes back to is this strain profile. Corresponding to a neutral axis depth. Which is C. That's the depth to our neutral axis. And it's going to have a value of your concrete, which is always going to be ECU. We always assume our concrete is failing. What we're not going to assume is the strain in our steel. So I'm going to select some value for my neutral axis. C. Going to have a strain of ECU. And some strain in my steel. This is going to result in, I never drew that in green before. Sorry. This is going to result in some compression stress, which I'm drawing in red for no good reason. Right, some compression stress in the top with a magnitude I'm not going to say what the magnitude is. And it has a distance. Actually, it always is the same. A beta 1C, magnitude F prime 0.85 F prime C. There is going to be some stress in my tension steel, FS, and there's also, right, I have some compression steel in there, and it's going to have a strain value of ES prime. It's going to be some stress associated with it. Best part. These I can resolve into forces with, right, force in my compression steel, compression force in my concrete, and tension force. Can I draw that? And my tension steel. This is all a summary from flexural design, flexural determining the capacity, right? Just a refresher. So I select a strain profile, I calculate everything. I'm going to calculate significant I'm going to select a couple special strain profiles to use. I'm going to do this on purpose. You could select 20 different strain profiles and do different points along the interaction diagram, but you're not going to do that. So if this is my moment axis and this is my axial load axis, it's easy to just select 6 points. We've already talked about, let's start out with 2 points. If positive is compression and negative is tension on my y-axis, I have P and O. This is compression only, axial load, no bending. My strain profile would look like, it'd be straight. It would be a vertical line. As opposed to this diagonal line here. Now I'm just making it ECU the entire way down. All in compression. The entire thing's in compression. It's at ECU because that is my ultimate strain in my concrete. So this will be your pure axial compression capacity. On the other side, I have tension only. Gonna call this PT. There, oops. So PT, not, there could actually be a moment associated with this, because if you're in tension, we're assuming our concrete isn't involved. So the only, if you're looking at your forces, your strain profile, you have the strain in your steel only. And your associated axial load with that is your yield stress times your 2 areas of steel. There could be a little bit of a moment if your 2 areas of steel are not equal. Let's see, so there's 6 points. Our one other point that we already talked about was our balanced failure. I'll put that out here. That is PB and MB. I just talked about that a second ago, or in the previous thing, but a balanced failure is when your concrete and your steel fail at the same time. So my concrete is at ECU, and my steel, and my tension steel is at EY. Another point that I can look at is the onset of cracking. That is, I'm going to put it right here. P crack and M crack. Onset of cracking means right when I start to have tension in my concrete. So the strain profile associated with that would look like that. ECU up at the top, strain in my steel is equal to 0, because if it strains just ever so much more, it's going to be in tension, and I'm assuming my concrete's going to start cracking. So 1, 2, 3, 4. My 5th one that I'm going to look at is, it's going to be down here. I'm going to call this PTC and MTC. Balanced failure is when I start to yield my steel. If you recall, there's also a point at which you become tension controlled in your fee, right? The transition, if you're below yield in your strain, you're compression controlled. If you're above yield plus 0.003, you're tension controlled. In between is the transition. It's talking about your fee factor. So this is my, oopsies, I should have written onset of cracking up here. I knew there was something else I should have written. This down here is my tension controlled. Which means my strain profile, I'm going to exaggerate that a little bit compared to the balanced. So I'm going to have my failure of concrete at the top. My strain in my steel is EY plus 0.003. Tension controlled, my fee, if you want to fee, is equal to 0.9. Oh, I should actually say balanced failure is when my strain in my steel is equal to yield. Go back and change that. ES is equal to EY. Tension controlled is when my extreme tensile steel is 0.00, EY plus 0.003. ES in the balanced failure, that's the strain at the centroid of your reinforcing of your tension steel. ET, remember, is the strain at your extreme tensile steel. These are two different locations of strain. Balanced failure is ES equals EY. Tension controlled ET equals EY plus 0.003. So I have 5, 1, 2, 3, 4, 5. You might notice the one I don't have is on my x-axis. I'm going to put it right here. This is my 0 MNO. Let's see. Did I write these backwards? I wrote the Y first. I wrote the Y and then I wrote the X. Oh my. That's funny. Okay, I just checked. That is because that's the way it is written in the book. Don't ask questions. The first number is your Y, the second is your X-axis. It is what it is. 0 MNO. That is our moment only, right? And you have to determine the C associated with to see that corresponds to this point. We don't know that one. That's why I saved it for last. Right? We have our axial compression. Oops, hold on, I'll let you all write that down. This kind of goes here. And this goes here. So we've calculated 6 different points. We have axial compression only, where the strain is equal to the compressive failure strain of concrete. Onset of cracking. Now my strain in my centroid of my tensile reinforcement is equal to 0. That's the onset of cracking. My balanced failure, where I fail in my concrete ECU at the same time as I yield my steel, that it's at the centroid, remember. The tension controlled, where my strain in my extreme tensile steel is the yield strain plus 0.03. That way I can use my 0.9 phi. I have my moment only. I don't know that point. I have to determine a C that corresponds to that point. It's not as obvious as the balanced failure tension controlled onset of cracking. And then I have my tension only, where basically the only thing holding my column together is my reinforcement, both compression and tension, because it's in axial only at this point. Now I get to draw a lovely lines between these. I'm going to draw straight lines, even though really, even though it's actually a little bit curved. This one, slightly different. Now I have my interaction diagram and my failure surface. These are only points. They're actually, if you keep increasing your strain in your steel, from onset of cracking through balanced failure, tension controlled, you're going to, if you find like 20 points along the way, it'll actually be more of a curve. But if you calculate these 6 points, you'll estimate it pretty well. So let's do an example. Okay, so our next, actually I'm gonna go to, okay, if you already printed now it's bigger. Okay, so this is our interaction diagram. If you already printed your notes, skip ahead a while, you're going to come to this page. This is how we determine our P and MN for an interaction diagram. So if we have our strain profile, right? That's an extreme one. Let's do a little less extreme. I don't want it to go through that center line. That's what I don't want. Okay. And let's see, we have our strain profile. It's got a C. We know the C, or we can figure it out because we've figured out ECU, and we have some sort of strain in our tension steel 1. We're going to call the bottom the tension steel 1, the top 2. Right now 1 is in tension, 1 is in compression, 2 is in compression. If our moment goes the other way, like seismic force, right, they could switch. So 1 is in compression, 1 is in 2 is in tension. For now, we're assuming this. So yeah, that's what that is right there. And this right here is the strain in our compression steel, ES2. This is going to result in some compression stress, right, in our concrete at a distance of a depth A and a magnitude 0.85 F prime C. We've also got stress in my tension steel and stress in my compression steel. I'm going to resolve these forces, or these stresses, into forces. Okay. Force in my compression steel, CS2. Force in my concrete. And then my tension force in my tension steel, TS1. I'm just calling them different things because if your moment, maybe your moment's only one way, maybe it's a seismic load and it varies which direction it goes. So I don't want to assume that everything is always in compression or everything is always in tension. Maybe it changes. And I'm going to locate these forces. This I'm going to call X. S1. This X, S2, the distance from the centroid to my force, the centroid of my force in my tension steel, XS1, distance from my centroid to my centroid of my compression, where the resulting compression force from my compression steel is, XS2, and then this little guy, XC. Distance from my centroid to the centroid where that compression force in my concrete is located, which is what? H over 2 minus A over 2. It's a height. We're talking specifically about the centroid, not the... we just need a place that we're going to end up taking our moment about, is what all this is. So, let's see. Pn, my axial capacity, is the sum of the forces in the steel plus sum of the forces in my concrete. Let's remember that positive is compression and negative is tension. So in this scenario, Pn is equal to the compression force in my concrete plus the compression force in my compression steel, which is CS2, minus the tension force in my tension steel, TS1. Hopefully that's greater than 0. Well, actually, if it's less than 0, then you're solely relying on your tension steel. C sub C and C sub S shouldn't be less than 0. Actually, never mind. Don't listen to me. C sub C shouldn't be less than 0. C sub S could flip to T sub S too. Right. What I'm saying is a concrete, it only has to be positive because my concrete's only good in compression. Let's just assume it has 0 tension capacity. So C sub C always has to be greater than 1. C sub S, let's say that this is all strain on the tension side. Then C sub S2 would turn into negative T sub S2 because it'd be tension up here in what you're thinking of as compression right now would actually be in tension. Probably confusing you even more by saying all that. This is just a general thought. My moment capacity is, I'm going to take the moment of these forces about the centroid. So, my moment is C sub C times XC plus C sub S2 times X sub S2 plus, right, if we're all, these are all causing counterclockwise, T sub S2 times X sub S, oh, it's 1, it's a 1. All 3 forces are causing counterclockwise moments if I take it about the centroid. Right. We've got up and over, and then up and over, down and over. All of those are counterclockwise. So this is our general process for determining our PN and our MN for our interaction diagrams. These are going to be our nominal capacities, not the next one. Okay, so we're going to draw the interaction diagram and we're going to determine PN and MN. And we're going to come back and add in our fees after we do this. So, first up, axial capacity. Here we have a square column with ties in it. It's got the same thing on both sides. Axial capacity. Compression. Should say compression. Earlier I said PO is equal to 0.85 F prime C AG minus A area of steel plus Fy times your area of steel. That's your axial capacity. This needs to change. If you go back, this needs to change to PO. We'll talk about why later. So let's see. AG, that's my gross area. I've got 16 inches by 16 inches. $256 inches squared. My area of steel. This is my total area of steel, not just one side or the other. I have 4 number 9s on one side and 4 number 9s on the other. So 8 times the area of a number 9. Number 9. That would be 1 inch squared. So 8 times 1 inch squared, 8 inches squared. So if I use my equation, my axial capacity is 0.85 F prime C, so 4 KSI, right? F prime C is 4,000, so 4 KSI times 256 inches squared minus those 8 inches that are actually made up of steel, right? I'm just getting the area of concrete, right? The gross minus the area of steel is all that is. This right here, area that's only concrete. 0.85 F prime C times my area of concrete, that's my gross cross-sectional area, minus my steel. That's the capacity that I get from concrete. My steel is 60 KSI steel. And 8 inches squared of that. You should get 1323.2 kips. So as my compressive axial capacity nominal. Well, we'll talk about what it means later. It's the point on the thing, on the interaction diagram. Okay, if I go down the list, let's see. Oh, I don't want that. Okay, let's do onset of cracking. Onset of cracking. What does my strain profile look like? And remember, this is the centroid of my steel. My strain profile for the onset of cracking is right when I reach ECU up here and ES here. That means that my C, my depth to my neutral axis, C equals D. D1, so 13.5 inches. If I draw my stress profile associated with that, right? .85 F prime C. It has a height of A. A, which is beta 1 times C. Beta 1, let's see, it's a 4,000 psi, so beta 1 is 0.85. Let's go back and write that, right? So, my concrete compressive force C sub C, right? It happens here. C sub C equals the magnitude, 0.85 F prime C times A times B. This is all back from, we've been doing this all semester, right? C sub C is 0.85 F prime C. That's the magnitude of the stress over the area over which it acts, which is A, the depth of that rectangular stress block, and B, which is the width of the beam or the column at this point. So that would be 0.85 F prime C, which is 4 KSI, A, which is beta 1 C, so 0.85 times 13.5 inches. C is 13.5 inches, times the width. This is a terrible, terrible drawing. Right? This is a lovely square cross section, 16 inches wide. So this is the same stuff we've been doing all semester. Now we just have an assumed strain profile instead of trying to guess what it is and going back and changing it. So C sub C, 0.85 F prime CAB. That should give you 0.85 times 4 times 0.85 times 13.5 times 16. 624.24 kips. 624 really, but we'll just keep it there. So that's my contribution to the strength from my concrete. Now let's look at the steel. The compressive steel has, let's see, we have to figure out, it's got a strain, right? ES2. This is 1 down here. Okay. CS2. That's the compressive force in my area of steel number 2. Right here. My area of steel number 1 isn't going to have any strain. So I need to figure out what the strain is so that I can figure out the stress. So I'm going to use similar triangles. Right. Determine my strain in my compression steel to calculate my stress in that steel. Going to use similar triangles. ES2 over C minus whatever this distance is. C minus D2 C minus D2 right, because that distance is, well, that distance is D2 is what I'm trying to say. This distance here to that strain, where's a good place to draw it? I should probably draw it here, is D2. So similar triangles, C minus D2 is equal to strain in my concrete over C. strain in my compression steel is ECU over C times C minus D2, 0.003 over 13.5 inches times 13.5 inches, and I need to find D2. If I go back and look, D2, 2.5 inches. So my strain in my compression steel is .00244. Now right now, if I just multiplied that by 29,000, I would get 70.9 stress, right? That's greater than my yield strain of 0.00207 because this is 60 KSI steel. Therefore, my stress is equal to my yield stress, 60 KSI. Concrete or my steel compressive force, if you remember. Why is this? See, if you take compression steel, you do your stress in your steel minus 0.85 F prime C. If you don't remember why, go back and review the compression. That is because up here we just used A times B, but really the area over which that 0.85 F prime C, you have to subtract out your concrete, or I'm sorry, you have to subtract out your bars area. We're doing it down here in the compression force, so that the centroids of those two forces coincide, and you don't have to, find out where the centroid is of A times B minus your area of steel up here. Go back and look at compression reinforcement to remind yourself why we're doing that. But this is what we're doing. So my strain or my stress in my compression steel minus 0.85 F prime C times my area of steel I've got 60 KSI minus 0.85 4 KSI AS2 is 4 number 9s, so 4 times 1.0 inches squared. That would give me 226.4. I extend it, will it get smaller? What the frick? Okay. What about my steel tension force? Well, my strain in that steel is equal to 0. Therefore, my stress in that steel is equal to 0. Therefore, my force in that steel is equal to 0. Why is this looking so weird? That's why. Okay. Sorry. Okay. So, oh yeah, I didn't go and look at it. Right. I have FS2, that's my compression force in my steel. That's the stress and then the compression force associated with it. So let's see, my axial load capacity. I'm going to sum up my concrete, right, PN is equal to my concrete plus my steel minus my tension steel. Concrete compressive force, steel compressive force minus my steel tension force, which is 0, so it doesn't matter. So let's see, C sub C, I had 624.24 kips. C sub S2, 226.4 kips. Minus 0 because there's no force in my tension steel. So you should get 851 kips. Now leave a little space in there because we're going to come back and add in the fee later. This is pure capacity. So let's look at my moment. I'm going to take the moment about the centroid. My nominal, I guess this is nominal, right? That's why I've got my little N in there. Actually take that away because we're gonna come back and factor it. So never mind. My moment capacity. I've got let's see, my C sub C, and it is acting at a distance. Let's see. This distance right here is A over 2, which is 13.5. That's my C. Right, my A is 0.85 times 13.5. I'm going to divide it by 2. .74. Right, that is A is 0.85 times 13.5. Beta 1 times C, 13.5 times 0.85. A is 11.48 inches. If I divide that by 2 from the top, is 5.74. Now this whole thing is square, 16 inches, right? Go back and check that, but right, 16 inches. So C acts at 8 inches, not C. The centroid of the section is 8 inches from the outer compressive fibers. So this distance right here is 8 minus 5.74, which should give you 2.26. So C sub C, 624.24 kips. C sub C times 2.26 inches plus my concrete or my steel force. This acts at right, I'm taking it from the centroid. So this was at D2, which is 2.5 inches. So from the centroid, 8 inches minus 2.5 inches, so 5.5 inches. Let's see, 624.24 kips times 2.26 inches plus 226.4 kips times 5.5 inches. Your nominal moment capacity should give you 2,656 kip inches, or 221 kip feet. So that is for one assumed strain profile. This one was the onset of cracking, so strain in my concrete is ECU, but I have no strain in my tensile reinforcement. So I only have forces associated with my concrete compression and my compression steel. Add those up and you get your axial capacity, take the moment about the centroid and get your moment capacity. Okay? Balanced failure. Did I? Let's see. Yeah, okay, so what I meant to do was take away all of these. I'll go back and update what I uploaded. Balanced failure. My balanced failure strain profile is when I reach ECU on my compression side and strain in my tension steel is equal to my yield strain. So what I have to do now is calculate my C. And it's going to look funny. So let's see. Find the C associated with this before. I didn't have to do this when I did my onset of cracking because my C was equal to my D. I didn't have to calculate it. I just had to say, oh, it's the same, C equals to D. So now I have to find it. All right, I'm going to use similar triangles here. Let's see, this is D1, which is 13.5 inches. So, C is to ECU as D1 minus C is to the strain, yield strain. If you simplify that, you get C is equal to D times, actually what you could do, I'm going to do this, as D is to yield strain plus ECU. So C is equal to D1 times ECU over EY plus ECU. So 13.5 inches times 0.003 divided by 0.003 plus 0.00207. should give you just about 8 inches. So it actually, C is going to correspond with my centroid. While I'm working on my strain profile, well, while I'm working on my strain profile, I might as well find a strain in my compression steel. Let's see. ES2 is to C minus D2, right? That's that little value right here, which was 2.5 inches. As ECU is to C. So the strain in my compression steel is equal to ECU times C minus D2 over C, 0.003 times 8 inches minus 2.5 inches over 8 inches. We should be right at yield, almost. Well, 0.00206. I'm going to calculate the stress associated with that. Oh, well, I'll calculate that in a second. Right? Yeah, let's do it now. My stress is equal to E times my strain. So 29,000 KSI times 0.00206, 59.8. So you're almost to yield. You're just before yielding. So not only are you yielding your tension reinforcement, but you're almost yielding your compression reinforcement. So I look at my stresses associated with this. I've got my compression block over my concrete, 0.85 F prime C. It acts at a distance, depth A, beta 1 C, 0.85 times 8, 6.8, 6.79. Got my stress in my tension steel, I'm sorry, this is my reinforcement steel, FS2, which is 59.8 KSI. And my stress in my tension steel, FS1, is 60 KSI because it's yield. This results in my forces. I've got C sub C and my compression steel, C sub S2, and then, I don't know, TS1. Might as well locate them while we're doing this. Let's see, C sub C acts at 8 minus 6.8 over 2, right? 16 divided by 2 minus 6.8 divided by 2 should be 4.6 inches. C sub S2 hasn't moved, 5.5 inches. Yeah, you'll see the only thing that moves where the force is the concrete force, right? Makes sense. Your concrete, your steel isn't changing the centroid, whereas the depth of your concrete stress block changes. As a result, the location of its centroid changes. Let's see, this is 13.5, so this is 2.5. 8 inches minus 2.5, this also happens at 5.5 inches. Remember, I'm locating my concrete compressive force, my steel compressive force, and my steel tension force in relation to the centroid of the section, the geometric centroid. So the location of the steel, because the centroid of the steel never moves, it's always going to be 5.5 inches from the centroid on one side and 5.5 on the other. Symmetric. In this case, obviously, it wouldn't be 5.5 all the time, but the location of the centroid isn't going to change. What's going to change is the depth of my stress block, and as a result, the location of its centroid. Right, you'll notice as I increased my strain from 0 to yield, my C decreased from 13.5 to 8 inches. So, yeah. Okay, so keep all this in mind. Let's see. I've got my concrete compressive force. C sub C, it is 0.85. F prime C A B, so 0.85. For KSI, 6.8 inches, that's the depth of my stress block. Width of my beam is 16 inches. get like 370 kips. My steel compressive force, C sub S 2. As my stress in my compressive steel minus that 0.85 F prime C. That's correcting for the area of concrete that's actually steel, times AS2, so 59.8 KSI minus 0.85 times 4 KSI times 4 inches squared is my compressive steel area. Should get 225.6. Let's see. My steel tension force, I'm going to call TS1, is equal to my, I'm assuming it's yielding, right? Yield times the area, let's make that a 1, that's a times 60 KSI times 4 number 9s, so 240, yeah, kills. So if I look at my axial load capacity, I got my positive concrete, my positive compression steel, and my negative tension steel. So 370 kips, 225.6 kips. Oopsies, how about I add things together? Plus. Minus 240 kips. $300. I'm just gonna round up to 356 kips. My moment capacity, Mn is equal to C sub C times that distance from the centroid to the centroid of C sub C, so 4.6 inches plus C sub S2 times 5.5 inches plus TS1 times 5.5 inches. So let's see, 370 kips times 4.6 inches plus 225.6 kips times 5.5 inches plus 240 kips times 5.5 inches. Four, 2, 6, 3. Or 355 kip feet. So that is associated with the balance. You see, we just followed the exact same procedure. We have a strain profile. From that, we have to come up with a couple numbers associated with my strain profile. We use that to calculate stresses, calculate forces, calculate capacities. Now, let's see, what's the next one? Tension controlled. Where'd my tension control go? Dude, where'd it go? Did I rip it? Well, let's draw it, right? We'll just wing it. Tension controlled. This is ground control to Major Tom. Oh, it's weird. Is that right? With 356 and 355. The axial capacity and the moment capacity are like almost the same number, obviously different units. Okay, tension control. I have the numbers. Tension controlled is very similar to balanced, because we're gonna have a strain profile like this. ECU is equal to 0, right? That's 0.003. My strain right here, actually, well, ES, since it's only one layer, my strain is equal to my yield plus 0.003. Again, let's see. I'm gonna let you guys work on it. Well, no, I'll do it. So let's see, find C. C C is probably going to be less than 8 inches because my strain is a little bit larger in my tension. See, this is my D1 is equal to DT. Find C. There it is. Okay, C is to ECU as D is to EY plus 0.003. So from that we should get a C of D times ECU EY plus 0.003. C 13.5 inches, 0.003. EY 0.00207 plus 0.003. Oopsies, plus ECU. That's right. Should give you a C of 5.02 inches. Well, let's see if I want to find my strain and my compression reinforcement. Let's see. ES2 is to C minus D2 as ECU is to C. This distance is D2, which is 2.5 inches. So let's see, 0.003 times 5.02 inches minus 2.5 inches divided by 5.02 inches. So my stress associated with that KSI 0.0015. .7 KSI. So we haven't yielded our compression steel, is what that's saying. We've beyond yielded our tension steel, we haven't yielded our compression steel. So let's see. have in terms of our stresses? We have our concrete stress, 0.85 F prime C. It happens over a depth A. Which is beta 1 times C, so 0.85 times 5.02 should be 4.27 inches. We've got our stress in our compression steel, which we just determined to be 43.7 KSI. And our stress in our tension steel, which is yield. Our resulting forces, we're going to have C sub C, compression steel force, and a tension force. We might as well go ahead and locate them. The steels don't change. They're still 5.5 because the centroid hasn't moved. C sub C now is acting at 8 inches minus 4.27 divided by 2. Right? H over 2 minus A over 2. So 16 over 2 minus 4.27 over 2, which should give you 5.87 inches from the centroid of this section. So let's see. Our compression force in concrete, C sub C. C sub C, 0.85 F prime C AB. 0.85, 4 KSI. What's A? 4.27 inches. 16 inches width. $232. Oops. My steel compression force. C sub S2 is 0.8. Oopsie, sorry. The stress in that steel minus the 0.85 F prime C, because we got to subtract out the part that is in concrete, times the area of steel 2. My stress, 43.7 KSI. Minus 0.85, 4 KSI times, it's supposed to be like a second one there, 4 inches squared. I didn't even write 0.85 times 4 times 4. 161 kips. My steel tension force, TS1, is Fy times my area of steel 1, because I've yielded my tension steel, right? We're beyond yield. We're over double yield, right? So 60 KSI times 4 inches squared. 240. I don't even have to write that again. It's the same thing as before. My axial load capacity. PN is my concrete plus my steel compression minus my steel tension. So 232 kips plus 161 kips minus 240 kips. It's not going to be a giant number, right? My moment capacity taking the moment about the centroid, C sub C times 5.87 inches. It's the distance from the centroid of the section to the centroid of the compression area, right? 5.87 plus my steel compression, which still acts at 5.5, and my steel tension, which acts at 5.5 as well. So let's see. 232 plus 161 plus 240 times 5.5. That'll give you 3,567 kip inches, or 297 kip feet. So far, for my onset of cracking, my balance condition, and my tension controlled, all I've done is the exact same thing. I assumed a strain profile. I had for tension controlled, and for balanced, I had to find a C. For my onset of cracking, where is it? For my onset of cracking, I know that C was equal to D1, the depth to those tensile, right? I had to calculate a C and a corresponding strain. For both, I had to calculate the strain in my compression steel and the corresponding stress. I can use all of those values to then find the force in my concrete, the compressive force in my concrete, the compression force in my steel, the compression force in my, or the tension force in my other steel on the other side, and add those together to get my axial capacity and my moment capacity. Yes. So, our final spot, we're going to ignore the tension because these are columns and they have compressive values. So I'm going to ignore the tension. My last point on my curve is my moment capacity. This is moment only. I am not going to draw anything because that's not where I start. My moment capacity means I have moment only. Therefore, Pn is equal to 0. What was my Pn equation? Pn is equal to my compression force in my concrete plus my compression force in my compression steel minus my tension force in my tension steel. For that to be true, I need my two compression forces to equal my tension force. C sub C plus C sub S2 is equal to my tension force. For this beam, my tension force will not change. There may be others where it is, but it probably shouldn't because we're in tension controlled territory. But this value does not change. Because it's always equal to, oopsies, I put a 2 and I should have put a 1. It is always equal to my yield times my area of steel. Right, if we go back all the way to this diagram, you'll notice I got a balance failure. I've yielded my steel. Now I'm way past yield. Probably have already yielded it here, right? So, going to iterate. Basically just start guessing. I'm going to make a little table. C sub S2 doesn't change. I'm sorry, C sub S2 changes. C sub C changes. They're both related to my depth of my stress block. So I'm going to guess a C. I'm going to guess an A. I'm going to calculate an A. Let's see, iterate. To find a C in which your compression force in your concrete and your compression force in your steel are equal to the tension force in your tension steel. So I'm going to have a C, a corresponding A, right? Beta 1C. prime C, a strain associated in my compression steel. Let's see, had that a minute ago. The equation for that, ES2 is equal to ECU times C minus D2 over C. That's going to have a stress Fs2 is equal to E times the strain, the elastic modulus times the strain, C sub C, 0.85, F prime CAB, CS2. Ugh, this is not going well. Running out of space. Got a C and an A. Strain. I'm gonna skip the stress. C sub C 0.85 F prime C AB. My steel is let's see, the stress, right, E times the strain minus 0.85 F prime C times the area of my steel. I'm going to add those together and compare them to T. Alright, which is always going to be 240 kips. So I'm just going to fill this out. If I guess a C of 4 inches, I got an A of 3.4 inches. A strain in my steel of 0.0011, 185 kips in my concrete, 116.9 kips in my steel. Together, those add up to 301.9 kips. Difference from 240. Right, let's see. T sub S. Let's see. My 100% difference, I'm going to do C sub C plus C sub C plus C sub S2 minus T sub S1 over T sub S1. So if I do 185 plus 116.9 minus 240, because that's how much I'm getting from my tension steel, divided by 240 times 100, I got a difference of 200 or 25.8%. That's really not good. Okay. What should I do? So let's see. My C sub C plus my C sub S is too big. What's probably going to drive it the most is my C sub C. If I decrease my C sub C, that'll decrease my, if I decrease my C, my depth to my stress block, that will decrease my A, that'll decrease my C sub C. So let's say C is 3.5 inches. Gives me an A of 2.98 inches. A strain of 8.57 times 10 to the minus 4th. A C sub C of 162 kips. C sub S2 of 86 kips. Add them together. 162 plus 86. 248 kips. So I'm 8 kips over. I want to be 240. Should write that there. I want to be 240. I'm at 248. So 248 minus 240 divided by 240 times 100. I'm at positive 3.3%. But just decreasing my C by 1/2 inch, I decreased my compression force in my concrete, my compression force in my compression steel, and I went from 26% over to 3% over. Okay, what if I go down to 3.4 inches for my C? Now my A is 2.89 inches. My strain in my steel is 7.94 times 10 to the minus 4th. My C sub C is 157 kips. My C sub S2 is 79 kips. Okay, now I'm at 236 kips. So I'm under. I want to be at 240. I'm at 236. 236 minus 240 divided by 240 times 100. I'm down 1.6 or 1.7. Okay. So what if I choose in the middle? I should get an A of about 2.93, a strain of 8.26 times 10 to the minus 4th, 150, or this is like 160. 82. Okay, that should give me 242 kips. Now I'm getting close. You can iterate as long as you want. 242 minus 240 divided by 240 times 100. I'm within 1%. So what did I do? If I look at let's summarize this. My moment only means that my nominal axial load capacity is 0. So my two compression forces have to equal my tension force. My tension force isn't going to change because my tension steel has yielded. So my tension force is always going to be my yield stress times my area of steel in tension. In this case, 60 KSI times 4 inches squared, 240 kips. Gonna iterate, gonna guess a C, gonna use those equations that I wrote. I hope there aren't any errors. Gonna use those equations that I wrote, guess a C, and go on from there. I iterated down to C equals 3.5 inches. What does that mean? Let's see. C equals 3.45 inches. So that's 2.5. It's like right there. In this case, my moment only, ECU, right? ES1 is equal to, well, it's greater than yield. We all know that. It's probably greater than, right, this is my ES2, which I found to be like what? 0.0008 0.26 instead of minus fourth. Let's see, my C right here. That's a generous 3.45 inches. Let's see, this gives me a stress of, let's see, 2.93. It's just past that. My A is 2.93 inches. My stress magnitude 0.85 F prime C. I didn't calculate it, but there's a FS2. Ignore that arrow. Right, Fy. I've got forces. I've got my C sub C is like way up here. My C sub C happens like way up here. C sub S, it's on that. And let's see, my TS1. As before, let's see. These, since the centroid never moves, 5.5 inches. 5.5 inches for the forces associated with my steel. This right here, H over 2 minus A over 2 is 8 minus 2.93 over 2. 6.53 inches. That's where my C sub C acts. So I'm going to right here. I don't have to calculate. I don't have to use this strain profile that I just drew. I'm just drawing it for illustrative purposes. I did need to find where my C sub C is for my forces, but I'm just drawing this for illustrative purposes because we already calculated all of our forces in this little table, right? Let's see, my axial load capacity. I've got Pn equals C sub C plus C sub S minus tension. So let's see, I've got 160 kips. Let me see, right? 160 kips plus C sub S2, 82 kips. Gonna subtract my T sub S, which is yield times the area, 240 kips. That's about 0. It's like 2, but that's okay. That's good because I'm on moment only. So let's see. My moment capacity. Mn is equal to C sub C times 6.53 inches. Did I put 5.3? Could be 5.4. I'll just leave it at 5.3. It doesn't matter. Plus C sub S2 times 5.5 inches plus T sub S1 times 5.5 inches. That should give you 160 kips times 6.53 inches plus 82 kips times 5.5 inches plus 240 kips times 5.5 inches. (2,815 kip inches) or 235 kip feet. Those are the values associated with axial capacity, onset of cracking, balance failure, tension controlled, and moment capacity. Super longest example ever, right? If you have any questions, I understand. Great. I'm going to stop here.